Let's start with shape distortion.
Yeah, I did.
All right, so the PowerPoints aren't very long for these two, and that's why I always put them in the same week, because the big term, the big quality factor that we are considering is distortion. So far this semester, the quality factors that we've talked about have been receptor exposure, contrast, spatial resolution last week, and now this week, distortion. And so we can break distortion down into size and shape. And so that's what we're going to look at this morning. The good news is that we will review next week in class. We will review spatial resolution, size, and shape, because your test will be open next week. Usually I only have it open Mondays and Tuesdays of that Thanksgiving week, but I will do it at least till Wednesday if that is better for y'all. I really don't want it going into the holiday weekend, because I'm not going to be checking emails every day, and if you have something go wrong, I just don't. So by Wednesday night at 11:59. I think that's fair, because we're going to have another whole review session on all that material next week. So all right, so shape distortion. The shadow of that fork, is that an accurate depiction of the way the fork really looks? No. So it is distorted. Sorry, turn the lights off. Come on in. I love your hair.
Oh my goodness.
That was awesome. Excuse me. Okay, so the definition of shape distortion is just a misrepresentation of the true shape of the object due to the relationship of the central ray, the part, and the IR. So we learn and we talk about these things in Yolanda's lab as well. That's why central ray placement and IR placement and part to the IR placement are important. Because if we don't pay attention to those things, then we can get this shape distortion that we're looking at here, and it is not an accurate representation of the anatomy as it truly is. So the difference between size and shape. So when we look at these three images here, in image A, let's say that is just a normal object. Okay, so it is a circle. Image B, the image measurement changes equally in both axes. So it's magnified, but still circular. So there is no shape distortion. So in other words, the distortion is happening in both directions, X and Y, equally. So that is not shape distortion. That is size distortion. Just the size of the object has been changed. In image C, the image measurement changes in one axis only. So shape, not size distortion. So in C, the long axis is what has been distorted. So that's why we have to distinguish between size distortion and shape distortion. So this cute baby right here, this is an old picture. He will be 5 next month. This was when he was a little less than 1. But that's my grandson. And you can see in this picture, he got a cute little face. That just makes me so happy. So that's him magnified, right? The picture is the same. It's just bigger. It's been magnified. It's been changed equally in both directions. Here, now his little head does not look like that, right? That is a misrepresentation. It's only been changed in one direction, right? So it is, think to your like pictures in a Word document or a text box in a Word document, if you grab just one side of that, what's going to happen? It's going to change in that one direction, right? So you're going to, so you have to be careful when you're looking at pictures and trying to make changes to pictures. If you want it to change equally in both directions, you're going to grab it at the corner, right? You're going to grab it at the corner and pull, and then the picture changes equally in both the X and the Y axis. In this case, I only stretched it out top to bottom. So that is shape distortion, not size distortion. Is that making sense? So if it's equally changed in both directions, that's going to be size distortion, not shape. Ooh, I just jumped on it. What in the world happened? So components of the ideal relationship are the relationship of the central ray to the IR. Y'all, that is not supposed to be doing that. I did not have. Okay, we'll just see here. The central ray to the IR, the object to the IR, and the central ray to the IR. So any misalignment of the central ray among these three factors alters the shape of the part recorded in the image. So that's why we say we want to produce the ideal relationship between those three things. And this is where mine and Yolanda's classes sort of overlap, which is good. The object we want parallel to the IR. Remember when we're doing like a PA hand, we want the part parallel to the IR. We don't want it jacked up unless we're intentionally doing an oblique, and we'll talk about that in a minute. But you want it to be part parallel to the IR, the central ray perpendicular to the part, and then the central ray would be perpendicular to the IR. In other words, we wouldn't want the IR to be at a tilt, right, to the central ray, because that's going to also create distortion. So we can even break down distortion even further. So we've said, okay, distortion is the big umbrella. We have size and shape. Now we're looking at shape. We can break shape down even further into foreshortening and elongation. So foreshortening occurs when the object is angled, but the central ray remains perpendicular to the IR. So in this instance, you can see that the central ray is perpendicular to the IR. However, the part is now propped up. Okay, so that means that the part is no longer parallel to the IR, right? Does everybody see that? Okay, so when that happens, we get what's called foreshortening. Sorry, it is just jumping around everywhere. So foreshortening just means that the object is represented shorter than it actually is. Foreshortened. So when Yolanda talked a week or so ago about internally rotating the leg on the AP proximal femur, that was to keep from foreshortening the neck of the femur. We wanted it so that we could see the actual neck of the femur. So elongation occurs when the central ray is angled or if the IR is not parallel to the part. So in the upper picture here, we see that the IR is not parallel to the part anymore. In the bottom picture there, we see that the central ray is angled. So we can get elongation either of those ways, with either angling the tube against the part, either direction, or y'all really think I had it set up to do that? I'm so sorry. I don't know what is happening with it here. So elongation's definition is just when the object appears longer than it actually is. And there's times, and we'll talk about this in a minute, there's times when we do both of those things because we want to see a part a certain way, but in general, we don't want to do that. We want everything, that relationship between the central ray, the part, and the IR to all be perfect so that we get the most accurate representation of that part. So beam centering is super important. And that's why we get so picky in Yolanda's lab about, okay, where is the central ray supposed to enter? There's a reason for that. And it's because the beam is cone shaped and the photons at the edge of the beam are at a slight angle compared with the photons at the center of the beam. And this is especially important for the joint space to be open. So what that statement is saying is that as the photons come out of the tube, they're diverging, right? So it's in a cone shape. So the photons that are in the very center of the beam are going to be the most perpendicular, right? The ones along the edge are going to be at a slight angle. So we want those that are the most perpendicular to be centered through, like, for example, the joint space. So you can see in this picture here, this is supposed to represent what it would look like if you're centered well to the joint space and if you're not. So in this picture here, this is just supposed to represent two parts, okay? Okay, I just got to take a deep breath.
If you take it out of this view and just in the other view where you can scroll down.
What you mean?
Like that. It won't skip around on you.
It just did.
Really?
Mm-hmm. I didn't touch it when it jumped just now.
What if you opened it through Blackboard? Like, and didn't actually open it up and just had it on like that preview view?
See, it just did that again. See, that wasn't me.
That is for advancer.
That's what I was
What
thinking.
is it?
Somebody's sitting somewhere with the
Who's
clicker.
messing with it? Who is it? See, it's jumping around even in Blackboard, so I'm thinking it's not. See, that's not me.
So it's a computer.
So, okay, we'll just deal with it. I just gotta take a deep breath and go with it.
And some other teachers sitting there going, I don't know why it's
I
not
know
working for me."
something's happening. Something is definitely happening. I don't even know if the clicker's in here today. Okay, so let's say that these are two body parts here, and this is the joint space between them. When we have the central ray aligned to where the central ray is entering right through the joint space, then that will image well, and you will be able to see that joint space. You'll be able to see through those parts. When you are off center of the joint space, now those photons that are sort of striking it at that slight angle that are not the most perpendicular, this is the way it's going to image, and it's going to be closed up. So that's the reason why we are so particular about where the central ray enters on a joint, whether it be wrist or toe or finger or whatever. We want it to be open. Now there's something called, I'm just going to sit right here so I can control this thing a little better, spatial distortion. So this occurs when either the part is rotated away from parallel or the central ray is adjusted to separate superimposed structures. So spatial distortion is when we use either foreshortening or elongation to our benefit. Okay, it's because we are trying to see a particular body part better. So when we talk about superimposition, then this beam here where the structures A, B, and C are all lined up on top of one another, this central ray alignment is going to project those body parts right on top of one another. So just a quick question, why is A showing up bigger than B and C?
Closer to the top.
Yes, because it's further away from the IR, right? It's further away from the IR. And so we're getting more magnification of that part, which is what we're going to talk about. I can't figure out which one is best to do first, shape or size. I've tried it both ways, but so magnification is what we're seeing in A. B is a little less magnified. C would be the least magnified. And that's not a real good, these are more ovals and that looks more like a circle there. That should look a little bit more like
Why
an oval.
is C on top? Wouldn't C be underneath A? Like it would,
Well, what it's showing you is that C is the least magnified. So if these structures, you would be able to see through all of them if we were talking about a real X-ray.
right, okay,
Does that make sense?
okay, yeah.
So it's not really that C is on top. They're all being projected one on top of the other. It's just that C is going to be the least magnified because it is closest to the IR. A is going to be the most magnified because it is further from the IR, has more OID. So in spatial distortion, when we're talking about creating spatial distortion by angling the tube, the part that's further from the IR is going to move the greatest distance. The part closest to the IR is going to move the least. And the part is going to move with the direction of the central ray. So you guys have already done some projections where you're angling. Okay, you've done your calcaneus and you've done tunnel knee where you've got those hard angles. And so we know that the part moves in the direction of the angle. That's what the bottom part is saying. The first line, the part further from the IR is going to move the most. The part that's closest to the IR is going to move the least. So in this picture here, that when I don't know what to say, y'all. I'm just sorry. Okay, I don't know what's happening. But if anybody has any other ideas, let me know. Somebody punking me?
Wait, can't you freeze the board? Like when the, isn't there an option to do that?
Don't know.
Like where it'll change on your computer, but you can keep it the same on the projector? Like freeze
I
it?
don't know. We're just gonna have to deal with it because I don't know. All right, so what this is saying is when we angle with beam one, and it's a little fuzzy, but beam one is over there on your left, and we have structures A, B, and C that are all lined up together. So for example, things like the heart and so the sternum, the heart, the spine, those would all be superimposed structures. Or the facial bones. You know, so you have your orbits and then we're just gonna quit here in a second. We don't want to, when we don't want to see things stacked up on one another, we need to be able to see those parts as separate. For example, the facial bones and that are typically covering the skull. We want to see just the orbits. When we use beam one and we angle, say, caudal, if that's the way the patient is, if their head is up there and their feet are down here and we angle caudal, then A moved the most, right? Because it is the farthest from the IR. C moved the least because it's closest to the IR. And you have the most distortion with A because it is moving the most and in the direction of the angle. Does that make sense? We're going to look at some images in lab this week that'll hopefully help you see that. And then if we were angling cephalic with beam 3, then again, A is going to move the most and it is going to be the most distorted because it is the furthest from the IR. C is going to move the least because it is the closest to the IR. So there's just less room for it to move when it's that close to the IR. So an example of which we've already done, no, we haven't either. That'll be, I believe next week, Yolanda will be starting shoulders. Well, with sections 2 and 3. So spatial distortion of the clavicle, you're going to learn that when we do clavicles, we do one that is perpendicular beam, just centered over the clavicle, and then we're going to do one that is angled, and that angulation varies. It depends. Your book, I think, teaches 30 degrees. Some places do 15, some do 20, some truly do 30. It's totally site specific with how much angle, but you can see the difference between these two images. Here's your one shot with the perpendicular beam, and see how it's sort of overlapping the top of the scapula here. Here's the one shot with an angle, and see how nicely it projects that clavicle up, and you can just sort of see that clavicle free of superimposition. Have any of you in the ortho places done clavicles yet? Seen a clavicle? Couple who, okay. All right, so they angle, right? They do an angle, and it just, usually they do two. They do a straight one and they do an angle. And that's so that you can just see the clavicle sort of free of anything else. You can also create that same spatial distortion by angling the part. And so, does everybody see how the clavicles are projected way above here? We call that, have y'all had that project? Did y'all get that projection when we did chest? Did Yolanda go over this projection when we did chest? Do you remember what that is called? Yes, apical lordotic, right? You purposely want to project the clavicles way above the chest so that you can see the apices of the lungs. And so you can get that by angling the part, the patient. See how the patient is leaning back? That's also the way your image will look if you have not properly sat the patient up when you're doing an AP chest on the stretcher and you leave them laying back too far and use a straight central ray beam. You'll also get that look. So that's exactly like what would happen if you had a patient on a stretcher and you didn't have them scooted back, to the back of the stretcher where they could sit up really straight. That's the way your chest x-ray will look. That's awful for a regular AP chest. Don't send that. That's terrible. You don't want it looking like that. Typically, you want the clavicles to come across the, where you can see about that much of the apices above. This is a very specific order if they're looking for like a pneumothorax or something. But typically, you don't want your chest to look like that. You can also get spatial distortion from angulation of the tube. So this one, we're angling the part. This one, we get the same image, but we're just angling the tube instead of the part. We get the same result. Practically, why would it be, like, for example, in this image, why would it be important to ensure that there's no shape distortion on this particular image? Yes, because of the fracture. And the ortho guys need to do what? Put it back together, right? And so when they are trying to align those bone fragments, they want a true representation of what they look like, because they want to put them back together where they grow back the closest to normal as possible. So you don't want there to be a lot of distortion on those images, and they're going to always do two images at right angles to one another. So it may not be too perfect, like it may not be a perfect AP and lateral, but it needs to be two done at right angles to one another so that they can, figure out how far to move the fracture, or if they're doing surgery and they're trying to put screws or plates or something like that in, they've got to make sure they get everything aligned well. And another example of clinically of when elongation might be used, and I know that you have not had fluoro procedures yet. That's coming next semester. But this is some images of a barium enema. Have anybody been involved in any fluoro procedures yet out there at all? Maybe a little bit, like if you're at Patewood and there's nothing going on in the routine, you may get in there some. So this is where barium is inserted into the rectum, and the image on the left, the sigmoid colon is sort of bunched up on itself, and we can do what we call an angled sigmoid that just sort of stretches that out and makes us be able to see that area of the sigmoid a little better. It can be done AP or PA. And one thing to know about when you are doing your angles, that your angle will be the opposite direction if you're going from AP to PA. So when we do clavicles here in a week or so, when the patient's AP, we angle cephalic, okay? If we turn them around to do PA, we would now angle caudal, okay? So when you go, if your angle calls for cephalic when they're AP, it's going to be caudal if they're PA. Something to remember. And Yolanda will probably get into that more with you later. A clinical example of foreshortening is when we do what projection of the hand? What projection is that on the right? The oblique. So we're purposely using foreshortening because we want to see it, the hand in a little different light. So there's times when we do use foreshortening or elongation clinically just to see different parts or see parts differently. This is an example of what I was telling you with spatial distortion where, and I know y'all have not had skull yet, but the image on the right is the head with the chin sort of down and the orbits and the facial bones in the skull are all superimposed on one another. We can do what we call a town projection where the patient is AP and we have a really hard caudal angle and it sort of throws the facial bones down. You can see here, all the facial bones are down here now. This is the bottom of the skull. This circular thing right here is your foramen magnum. So it's just a way to be able to see the back of the skull, top and back of the skull without all the facial bones covering it up. So you will get to that. Y'all get to skulls in the summer. So let's go out of this one and see. Ooh. Size distortion. Hopefully it behaves. So size distortion, we talked a little bit about in the first part of that shape, is where an image is magnified equally in both directions. Okay, and you've seen this picture before. This was in spatial resolution PowerPoint last week. So let's talk more about it. We were focusing on the spatial resolution of the shadow last week. This week, we are focusing on the size of the shadow. Okay, so misrepresentation of the true size of the image as compared to the object. We can use size distortion and the term magnification interchangeably. So when we talk about size distortion, if I use that, I'm talking about magnification. We can just use them interchangeably. So when you look at this image of the pencil, and when it has a lot of what? This is our source object image. What do we have a lot of here? OID. We have a lot of OID, object to image distance. As we decrease that OID, what is happening to the shadow of the pencil? It's decreasing. It's getting smaller. And so this week in lab, you're going to do some activities where we're going to shoot some images, but we're also going to do some activities where you're just purely looking at shadows of objects to see what's happening to the shadow of the object as you increase or decrease OID, as you increase or decrease SID, and how that affects magnification. So again, to review your distances, your SID, so your source to image is made up of your source to object and object to image. So SOD plus OID equals SID. So you still got to remember that, because now we're going to talk about how do those distances affect magnification of the image. So just a few little things to remember is that X-rays travel in straight lines. We know that from about week 2, we talked about that. X-rays diverge from a source, from the focal spot in the anode. The focal spot is not a point source, meaning there is not just one spot on the filament where the, on the anode where the photons are created, right? It's an area, and that area is affected by the size of the filament that we choose. So if there were just one spot that the x-rays were created from, then remember we would have no unsharpness, right? Because they would be coming from just one spot. But remember looking at your finger in relation to, shutting one eye, and they come from an area instead. So we can use the law of similar triangles when we're talking about size distortion. So all radiographs have some magnification due to the relationship of the focal spot, the object, and the receptor. And the reason is similar to the light spread with inverse square law, which we've already talked about. So when I say that there is always some magnification, it's because of the divergence of the beam. Okay, so the object can't be projected smaller than it actually is. Does that make sense? Just physically from the way the beam is created. It's spreading, right? So your image is always going to have a bit of magnification. Even if we have the part as close to the IR as possible, there's still going to be a little bit. So that's what that statement was talking about. OID is your major factor that controls magnification. OID has a greater impact on magnification than does SID. And we know that as OID increases, magnification increases. That's why we want to get the part as close to the IR as we possibly can. We want there to be minimum OID. When you're doing your lateral chest on the stretcher, you want to try your best to get the patient as close to the upright bucky as possible, because you've probably seen that now as you're out in clinic. Makes a big difference. You have a gap like this, it's going to magnify that chest even more, and there's a good chance that you're going to do what? Have to repeat it because why? Huh? Yeah, it's not fitting, right? It's not going to fit. It's too big for the size of the IR. So it makes it, so OID is the major controlling factor of magnification. We're going to see that, and you can see that in the image there, the size of the object as displayed in that image is much larger with that greater OID that's on the left than the shorter OID that is on the right. Now, SID also does affect magnification, but not to the degree that OID does. In this week in lab, we're going to show this. We're going to do some images with a big OID, and then we're going to do some images where we change the distance, and you're going to see that it only takes a couple of inches of OID to make a big difference in magnification. Whereas if we just change our distance, our SID a couple of inches, you may or may not even really, with just our eyes, see a difference. It takes much bigger difference in SID to see that. But as SID increases, magnification decreases. And the way, again, that you can remember this is think back to why do we do chest x-rays at 72 inches? Because it decreases magnification of the heart. So if you start getting confused about, oh, these are hard to remember, think about, okay, chest x-rays at 72 inches because it decreases the magnification of the heart. We have to use standard SIDs because we can't physically get 72 inches over a table for a hand to get better spatial resolution and less magnification. So standard SIDs are typically 72 and 40. But that can change if clinically warranted, meaning you can't physically get 72 inches for whatever reason. Or you can't truly get 40 inches because the patient is in a traction bed or something, and you're having to go underneath the traction bar, and you're lucky if you get this much distance. So there's things clinically that can cause us to change that. But all right, so for this semester, the last of the formulas, okay, that you got to know. Last of the formula. So we're going to talk about how do we calculate magnification. And we see that we can do that with putting the image size over the object size or the SID over the SOD. And we can do that because of the law of similar triangles. And so we know that with the law of similar triangles, this triangle right here and this triangle are going to have in these corresponding angles, those angles are going to be congruent and the sides are going to be proportional. Okay, so that's why we can use the law of similar triangles to determine how much magnification there is in an image for the true size of the object. So for example, if we put the image size over the object size and we put it in a ratio that equals the SID over the SOD, we can calculate any of these if we have 3 out of the 4. Okay, so if the SID is 30 and the OID is 15, what is the object size if the image is 2 centimeters in diameter? So we're simply just going to plug in what we're given, okay? So we're saying we're asking for what is the object size. So object size is our unknown. That's what we're looking for. Our SID is 30. We can put that in. Our SOD is 15. And our image size is 2 centimeters. So when we plug all that into our formula, we get that our object size is actually 1 centimeter. Now, we could have done that in our heads, right? Does everybody realize that 30 over 15 is 2? So we know that the object was actually magnified by a factor of 2. So it would really only have been half what the image size was. But in other words, if you have 3 out of the 4 of this information, you can put it into this ratio here. This is just a ratio, and figure out what the actual object size is. Okay, so we're going to talk more about that in lab as well. Magnification factor just simply tells the radiographer how much larger the image will appear on a radiograph as compared to the object. So we have to consider the size of the monitor, okay? So that's where it can get a little bit tricky, a little bit confusing to you. You say, well, you said that the image could never be smaller than the actual object. That is true, okay? That statement is still true. But it depends on the size of your monitor as far as like physically looking at the size of the image. Does everybody follow what I'm saying? Like if your monitor is this big, like this tablet, then certainly it's you're going to look at it and it's going to be smaller than what your actual object is. That's because the monitor is not, we don't have a gigantic monitor in here that's like the size of this wall that would make it, when you're looking at the part, like body part compared to what you're seeing here on the screen, the physical size of it on the screen. Does that make sense? So we're going to actually do an activity in lab this week that'll help us hopefully understand that. If you're trying to calculate magnification factor, you can just put SID over SOD or image size over object size. It depends on what information you're given. We are typically going to be using SID over SOD to calculate magnification factor because that's really easy, right? You're going to be given your SID, you're going to be given your either your OID, so you can calculate SOD, or given SOD. So it's a real easy calculation. So this is where we are. So calculating the size of an object based on magnification factor. So if you have your magnification factor, you can determine the actual size of your object based on the magnification factor. So again, all we're saying with magnification factor is by what factor has the object been magnified in the image. That's what we're talking about. So in this case, the object is 4 by 1. Okay, so we're saying the object is 4 by 1 and the magnification factor is 2. So what are the measurements of the image? So we could figure out what the actual image size would be based on the fact that our magnification factor is 2. So really all you're saying here is the object is magnified in both directions, right? By a factor of 2 in this case. So we just multiply 4 times 2 and 1 times 2 and get 8 by 2. Easy, right? Seems too simple, but that's all there is to it. So we can also talk, so far we've said, okay, magnification factor sit over side or image over object size. That's the way we can figure out magnification factor. We can also talk about percent of magnification. All right, so if we talk about percent of magnification, we can say, okay, if our image is 10 centimeters, our object is 8, because we know that our image is always going to be slightly larger than our object, has to be because of the divergence of the beam. We talked about that earlier. We can calculate the percent of magnification just by taking the image size minus the object, dividing it by the object, and multiplying by 100. Anytime you're trying to figure out a percent, you're going to multiply by 100. So in this case, going back to the numbers that we were given here, we can say 10 minus 8 divided by 8 times 100, or it was magnified 25%. There are 3 ways to write that, okay? They all are going to give you the same answer. It's just 3 different ways to write it. So you can say image size over object size minus object size over object size times 100. That's one way to write it. You could say magnification factor minus 1 times 100. Why does this work? Somebody tell me why this works based on this. Why can we write
Object size over object size, assuming 1.
right? And image size over object size is what?
Your magnification
Yes.
factor.
So all 3 of these formulas, percent magnification, if you broke this formula down written like this, you would say image over object minus object over object times 100. Because remember, anything that's in the denominator, you have to divide everything above that line by the denominator, right? So this is just written this way, the long way. Everybody follow? And then this is just taking this formula and saying, okay, well, image size over object size is magnification factor, and anything divided by itself is 1. So that's why you can say it's all going to give you the same answer. So depending on what information you're given is going to help you determine which way you want to use the formula, which formula you want to use, in other words, when you're talking about calculating percent of magnification. We're going to get a lot more practice with this in lab this week. So if you don't quite get it, don't panic. We've got more time to deal with it in lab. So we said earlier, the 4 radiographic quality factors that we have addressed this semester were what? What was the first thing that we talked about like about week 3? And I said them earlier today.
Didn't you say KVP? You're talking about all the stuff
Well,
listed at the beginning of class.
Yeah, so what does KVP control? Okay, contrast is one of them. What was before that? Receptor exposure. What did we talk about last week? Spatial resolution and then distortion. That's the 4 big radiographic quality factors that we cover in my class. Okay, so SID, so source to image distance, affects distortion, receptor exposure, and spatial resolution. Does SID affect contrast? No, because SID does not affect the quality of the beam. So SID does affect size distortion, right? We just talked about that. It affects magnification. OID affects distortion, right? Size distortion, we talked about that. It definitely affects spatial resolution. We talked about that last week. OID also affects receptor exposure and contrast, but that's only when we have an air gap. So like an OID of 6 to 10 inches. We're going to talk more about that next semester. For right now, what I want you to understand is that OID truly does affect all 4 radiographic quality factors, but only if it's an air gap, like a 6 to 10 inch OID is where you're going to see it have an effect on receptor exposure and contrast. The least amount of magnification is achieved with a short OID, so getting the part as close to the IR as possible, and a long SID. Well, we have standard SIDs that we use because we can't physically get 72 inches over a table. But if we could, we would get less magnification at 72 inches than at 40. Does everybody follow that? Okay. Any questions? We're going to get more practice with all of that in lab. And then we're going to review all of this material and spatial resolution next week. Okay? Because next week you will have your final practical. Get that done before Thanksgiving. Okay. Let me stop sharing for a second. All right. So let's do this next. Let's go over this chart and talk about spatial resolution. So hopefully you brought your paper, or you can pull up your lab manual and we can look at activity 5 and talk about how these things in the column on the left affect spatial resolution, unsharpness and spatial resolution. So unsharpness and spatial resolution have what kind of relationship? Inverse. If unsharpness goes up, spatial resolution goes down. Okay. So let's start here and look at each one of these. And if you have a question about it, then certainly raise your hand and ask while we're going through it. And then lastly, I'm going to stop the recording and then we'll go through the AEC test. Okay. So let's see here. We don't have enough for everybody to have to answer, so I won't do that. I was going to ask, but we won't. All right. If focal spot size increases, so our focal spot size is getting larger, what happens to unsharpness? It increases, right? The larger the focal spot, unsharpness goes up, so spatial resolution goes down. Any questions about that? Larger focal spot means that unsharpness is going to increase, therefore spatial resolution is going to decrease. All right. If OID,
Wait, I thought the last one got smaller. The focal spot got smaller.
we're on the focal spot increasing.
Oh, yeah.
We're just in the chart.
Oh, I'm looking at the wrong chart apparently.
You might have been looking at that first activity where we did the math.
Oh,
Yeah.
I see.
Yeah. So focal spot goes up, unsharpness goes up, spatial resolution goes down. If OID decreases, what happens to unsharpness? It goes down, and what happens to spatial resolution? It goes up. That's right. That's why we want the part to be as close to the IR as possible. If mass increases, what happens to unsharpness? Nothing. Those are there for a purpose, not to just trick you, but to help you understand. So changing the mass has absolutely no effect on unsharpness. What's recorded in the image. Did anybody not understand that? So changing the mass does not affect unsharpness, therefore it does not affect spatial resolution. No change. Okay. SOD decreases, and I'm qualifying that by saying the OID remains unchanged. So what if SOD decreases and OID does not change? What also had to change? Who said it? Delisha. She's back there like, yes. So SID also changed. So if SOD decreases, what does that do to unsharpness? Increases it, so spatial resolution decreases. Does anybody need me to draw that, or does everybody understand this distance thing? You understand it? Okay. So KVP, does it have an effect on unsharpness or spatial resolution? No, it does not. It does not change what is recorded geometrically in the image. Okay, so no change. If SID decreases, what does that do to unsharpness? Increases in spatial resolution? That's correct. Now, if the focal spot gets smaller, what does that do to unsharpness? Decreases it. So spatial resolution increases. OID gets larger. What's that do to unsharpness? Increases it. Spatial resolution. Yes. Here's another one with SOD. If SOD increases, but the OID does not change, what also increased? SID. Yes. So if SOD increases, what does that do to unsharpness? Decreases it, and spatial resolution increases. And again, if SID increases, unsharpness decreases, spatial resolution goes up. So one thing that you can hopefully understand and commit to memory is that if SOD or SID increase, it has the same effect. Okay, so increasing SOD or increasing SID both make unsharpness go down, spatial resolution go up. So what I'm trying to say is if you increase SOD or SID, it has the same effect. If you decrease SOD or SID, it has the same effect on unsharpness and spatial resolution. So any questions about that? One thing you can also think about is how do we write unsharpness formula? What makes up unsharpness formula? So if we have unsharpness, that's not going to write very good. Focal spot size
Multiplied by OID.
multiplied by OID divided by SOD. So look at what makes up unsharpness. That's why we can say focal spot size affects unsharpness. OID affects unsharpness. SOD affects unsharpness. These two together make up what?
SID.
My pen is not right. SID. So SID affects unsharpness. So when in a couple of weeks when we're reviewing for the final exam, you're going to have a chart to look at that's going to include all of these things. And it's going to say, if this does this, then what happens to the 4 quality factors? So we're going to put it all together. Comprehensive study tool. So think about what makes up these different things. What makes up magnification factor? What do we say magnification factor? What's the easy one I said to remember how to figure out what magnification factor is? What are the 2 things that you can put over in a ratio?
Image size.
SID over
So yeah, so SID over SOD or image size over object size. So SID over SOD. So we know that SID has to affect distortion, meaning size distortion, right? SID, SOD make up, SOD and OID make up SID. So we know that all 3 of those distances affect size distortion. So look at, look, if you get confused, look at what makes up, how we're calculating if there's a difference. There is not, and we'll talk about this in lab, but there is not a calculation for shape distortion. Like we don't have a formula to determine how much shape distortion there is in a part. So we just know that it's based on the relationship of what three things to determine if we have shape distortion. The relationship of what? What? So the relationship of the IR to what? The central ray to what? The part. So think about the sandwich analogy that Yolanda gave you back at the beginning. You have your central ray, your part, your IR. You want all of those to be aligned perfectly so that you get the most accurate representation of your anatomy possible. But for shape distortion, we're not going to have a formula. We're just going to talk about it. Okay, was the central ray perpendicular to the part? Was the part parallel to the IR? Was the central ray perpendicular to the IR? If that's true, then you will not have shape distortion. Except at the very edges, but we just don't really consider that because there's nothing we can do about it. And we have a little bit of shape distortion at the edges because of what? Not scattered. The divergence of the beam. The natural way the photons come from the X-ray tube in a cone shape. So those photons along the edge are going to strike the object at a slight angle. So it's going to create a bit of shape distortion no matter what we do. But we just say there's not if we have all three of those in alignment. Okay, let me stop the recording.